was finding max. To the Tennessee waltz went an old friend I happened to see. I introduced her to my loved one, and while they were doing calculus, my friend stole my sweetheart from me. And I remember that night and the Tennessee waltz. Only you know how much I have lost. But instead I have found how to calculate the min and max of a function defined on a closed bounded set. Alright, so what we will do in this video is study the extreme value theorem for functions of two variables and how it can be used to solve optimization problems. One of the main reasons for finding maxima and minima of functions is to solve optimization problems. So if we go back to functions of one variable, pretty often we're interested in optimizing the function, which means finding its maximum or minimum value, but over a closed interval. So we think of the function as being defined with domain given by a closed interval. And when this happens, then things are really nice because we don't need to use, for example, the second derivative test to determine whether critical numbers are local min and max. We can use a very important result called the extreme value theorem, which simplifies the calculations quite a bit. So let me just recall how this goes in one dimension. So let f be a continuous function, so that's an important assumption, but in most optimization problems, this is satisfied, which is defined on a closed interval a to b. In such a case, there is this important result called the extreme value theorem that says that f must have an absolute maximum and minimum somewhere over the interval. It must have an absolute min and max. And we know where this can occur. So it could either occur at a local min and max, which must be at a critical number of the function, or it could be at the endpoints of the interval. So that gives a very natural strategy for optimizing a function over a closed interval, which goes in 3 steps. So the first step is to evaluate the function at its critical numbers. So if the absolute min and max occurs at a local min and max, this must be at a critical number. It is not true that all critical numbers are local min and max, but local min and max must be at critical numbers. So that's the first step. Second step is to evaluate the function at the endpoints of the interval. And the third step is to put all these values together, compare, and pick the largest. The largest of these values will be the absolute maximum value of the function over the closed interval, and the smallest one will be its absolute minimum value. All right, so this is the natural strategy for optimizing functions or finding maximum and minimal values of functions over closed interval. Now, what we want to see is whether we can generalize that to the 2 dimensions. And the most important thing is to generalize the assumptions, which were that the function is continuous and that it is defined over a closed interval. Now we have already generalized what it means to be continuous in 2 dimensions, so that's fine, but now we need to generalize what it means to be defined over a closed interval in 2 dimensions. So we need to define what replaces the idea of closed intervals in 2 dimensions. So let D be a set in R2. So first I need to define the idea of boundary points for a set. So a boundary point is a point such that every disk which is centered at this point will contain points that are inside the set and points that are outside the set. So if I have a curve here, a blue curve here in R2, and I take my set to be all the points inside the curve here, then the boundary points of the set will be precisely the points on the boundary. Because if I have a point here on the blue curve, and if I sketch any disk around this point, then there will be points in the disks that are outside the set and points that are inside the set. So this is a boundary point for the set. And then we say that a set D in R2 is closed if it contains all its boundary points. So here, if the set was given by all the points within the curve, then it would be closed if all the points on the blue curve are also included in the set D. So that's the first idea that I need, the concept of closed sets. And the second idea I need is the idea of bounded sets. So we say that a set is bounded if it is somewhat of finite size. More precisely, we say that it is bounded if it is contained within some disk So that means if you can draw a disk in R2 and that the set is contained within the disk, then the set is bounded. So what replaces the idea of closed intervals in 2 dimensions is the idea of closed bounded sets. With these definitions under our belt, we can now state the extreme value theorem for functions of 2 variables and explain how it can be used to solve optimization problems. So let f be a continuous function on a closed bounded set D in R2, then the extreme value theorem states that f must have an absolute max and an absolute min somewhere in the set D. Now this is precisely the same statement as in 1 dimension. And in fact, we know even more. We know that the absolute min and max can only occur at 2 different places, either at a local max and min or at a boundary point. And we know that all local max and min must occur at critical numbers. Not all critical numbers are local max and min, there's also saddle points, but all local min and max are critical numbers. So that gives rise to a very powerful strategy for solving optimization problems, which is pretty much exactly the same as what we had in 1 dimension. So it goes in 3 steps. The first step is to evaluate the function at its critical numbers in the set D. The second step is now to find the extreme values of f on the boundary of D. So in other words, you want to evaluate f at all the boundary points, but now it's probably going to be a continuous boundary, like a curve. So you need to find the extreme values of the function on this boundary. And the last step is to compare all of these values and pick the largest, which will be the absolute maximum value of the function on the set, and the smallest, which will be its absolute minimum value. So that gives a very powerful method for solving optimization problems when the function is continuous and defined on a closed bounded set. Let me conclude this video by working through an example. So suppose that you want to find the absolute minimum and maximum values of the function x squared minus 4xy plus 8y on the set D, which is defined as being given by all the points in R2 such that x is greater or equal than 0 but less or equal than 3, and y is greater or equal than 0 but less or equal than 3. So the first step is to make sure that the set is bounded and closed so that we can use the extreme value theorem. So here I'm taking all the points with x between 0 and 3 and y between 0 and 3. So the set D is a square here, so it's all the points within the square but also including the boundary, because I'm taking the inequalities to be less or equal than and greater or equal than. So that is a closed set because it includes its boundary, and it's also bounded because it has finite size, so it can be contained within a disk. Okay, so we have a closed bounded set, so we can apply the strategy that uses the extreme value theorem to find the absolute minimum and maximum values, because we know that there must be an absolute minimum and maximum values over D. So the first step here is to find the critical points, critical numbers, and evaluate the function at these numbers. So remember that to find the critical numbers, we have to calculate the partial derivatives with respect to x and y and find the points where both vanish. So the partial derivative of the function with respect to x will be given by 2x minus 4y. So this will be equal to 0 if x is equal to 2y. And then the partial derivative with respect to y is given by minus 4x plus 8, which will be equal to 0 if x is equal to 2. So if we combine these two conditions, we want both partial derivatives to vanish. That means there's a single point here where they both vanish, which is at x equals to 2 and y is equal to 1. So that is the only critical number, and it happens that it is included within our set. It's somewhere like here, so it's good. So it is in the set, so we need to consider it because the absolute max or min may be at this critical number. So what we need to do now is evaluate the function at this critical number and then just keep track of that value so that at the end we can compare with all the other possible values and see whether it's an absolute min or max. So the function here at the point x equals 2 and y equals 1 is given by 4 minus 4 times 2 times 1, so that's 8, plus 8 times 1, so it gives a 4. So I'm going to put that in green so we can, oops, that's not green, let's go back. put this in green so we can keep track of it. Okay, the second step is to now look or evaluate the function at the boundary and find the extreme values of the function on the boundary. So find the maximum and the minimum values of the function on the boundary. So here the boundary you can really split into 4 parts because it's really given by 4 lines. So L1, L2, L3, and L4. So we can try to find the maximal and minimal values on each of these line segments, and then we can compare to find the extreme ones. Okay, so let's first look at L1. So this is the line which is given by y equals to 0. So now I'm trying to find the maximum and minimum value of the function on that line. So I can substitute y equals to 0. I get a function of a single variable, which is simply x squared. And now x is, of course, between 0 and 3. So now I want to find the maximum and minimum value of x squared between 0 and 3. Well, x squared is an increasing function, so the minimal value will be at 0, in which case it is 0, and the maximal value will be at 3, in which case it will be 9. So I'm going to take my green color, circle those, keep track of these values. All right, so I have to do the same thing for all 4 line segments. So for L2 here, then I have x equals to 3. So now the function of one variable that I'll get is f with x evaluated at 3. So here I'll get 3 squared, so that's 9, minus 4 times 3, that's 12y plus 8y. So that is 9 minus 4y. And of course, y is also between 0 and 3. All right, so what are the minimum and maximal value of that function over this line segment here? Well, this is a decreasing function. So the minimal value will be at the point where y is the largest. So it will be at f(3,3). And if I evaluate the function at f(3,3), I get 9 minus 12, gives me minus 3. And the maximal value would be at 0, so where y is 0, so f(3,0), which gives me 9. So again, I'll just keep track of these values for later. Okay, and then I need to keep going, so I have 2 more line segments to do. L3, so if I go back to my picture, L3 was the case where y was equal to 3. And I substitute that in my function to get the function of one variable that I'm interested in. So the function here was x squared minus 4xy plus 8y. So if I substitute y equals to 3, I'll get x squared minus 12x plus 8 times 3. So that's 24. All right, and then I need to find the maximal and minimal values of that function over the interval given by x between 0 and 3. Now this is a quadratic function, so it's a little more complicated. So what we have to do now is just use the extreme value theorem again, but for functions of one variable, because this is a continuous function of one variable defined over a closed interval. So I know that I must have a max and min over that interval. It can be either at the endpoints or at the critical numbers. So I have to check whether there's a critical number here. Now, if there is a critical number, it would be given at the 0 of the derivative. So I'll think of that as a function of one variable g of x. If I calculate its derivative, I'll get 2x minus 12. And if I set this to 0, I get that this will be at x equals to 6. So there is a critical number for that function at x equals to 6, but this is not in our closed interval. So this is not in the interval, so we don't have to care about the critical number in this case. So we know that the min and the max must occur at the endpoints of the interval. So we don't know which one is which, so let's just evaluate and we'll see. So here at x equals to 0, I get the function evaluated at 0 and 3, so that should give me 24. And at x equals to 3, then I'll get 9 minus 3 times 12, that's 36 plus 24. So that's 9 minus 12, so that's minus 3. So I see this is the min, and this is the max. on this boundary line. So I'm just going to keep track of those in green, 24 and minus 3. All right, and there's one more line left for the whole boundary. This line was the remaining one, which is at x equals to 0. So here the function will be f of 0 y. Now looking back at the function, if I set x to 0, I'll get just 8y, with again y being defined between 0 and 3. So this is an increasing function, so the minimum will be at 0, which is just 0, and the max will be at 3, which will give me 24. So I keep track of these values again. All right, and then I can just take all of these values together and compare. So if you look at all these values, there's 4, 0, 9, 9, 9, this is the same point, minus 3, this is the same point, 24, this is the same point, and 0 is the same as there. So the largest of all of them is 24, and the smallest is minus 3. So I've found the absolute minimum and maximum values. So the absolute maximum value is 24 at the point 0, 3, and the absolute minimum value is minus 3 at the point 3, 3. And that solves the optimization problem. So the steps here are exactly the same as what you did for functions of one variable, but because the boundary is more complicated than for a closed interval where you only had 2 boundary points, 2 endpoints, here it's a little more complicated. You really have to evaluate the value of the function everywhere on the boundary, pick the largest and smallest so that you can compare with the value of the function at the critical numbers. So it requires a bit more work, but the steps are the same as what you did for functions of one variable.